Hello everyone, this is Jeon Peol-jung. We are studying Introduction to Data Structures. Today we are studying quicksort, divide and conquer, recursion. This figure shows the idea of quicksort, the ordering of a list with quicksort. Basically, the document, the title is A blah blah G. We divide the two parts. The boundary is L, boundary M. So from A through L document is left hand side. And the other part from M through G case we can divide the right hand side. And then recursively we also divide A through L into A through F, G through L. So we two part, okay? Similarly, right hand side, M through G partitioned into two parts from M through R, from S through G. So similarly, we can repeat until the lip node becomes one paper sheet, okay? And then once this kinds of partition, we are done, okay? So in that case, we don't need the merge stage, okay? So 3 steps at divide and conquer, combine. Divide case, the problem is divided into multiple sub-problems that have the same structure with the original problem. The conquer, the sub-problems are conquered by solving them recursively. Combine, the solutions to the sub-problems are combined into the solution to the original problem, like merge sort case, merge stage. So recursion tree for time complexity divide conquer case, time complexity Tn for input size n into 2 sub-problems. Each sub-problem input size m n over 2, and then this one is the combined cost. So original size Cn, this is actual combined cost, and then into two parts sub-problems. The input size is becomes n over 2 and another n over 2, right? So merge stage 2 sub-problem is the combine this one, sum is Cn. Similarly, we can repeat again and again. The depth or height of the tree, this one is log 2n. So total cost is log Gn times Cn plus, okay, this one. So divide cost is Cn. So we just focus on Cn times log n. This one is zeta and log n. So introduction. Quicksort is regarded as the best practical sorting algorithm. Was developed by British computer scientist Professor Tony Hoare in 1959, and this algorithm paper published in 1961 in ACM Communications Journal. On the average, it is remarkably efficient with the expected learning time, zeta and log n. The constant factors hidden are quite small. Actually, its worst case learning time is zeta n squared. It also has the advantage of sorting in place. It rearranges the numbers within the input array. So this is the original quicksort algorithm published in Communications of the ACM, Volume 4, Issue 7, July 1961. 2 algorithms. Algorithm 63 is a partition, and algorithm 64 is a quicksort. So you click this link, you can take a look at the paper. So this part is quicksort part. You can see partition, quicksort recursively. Recursion is used. And the partition is important function previously. You can see before recursively call two quicksorts, and the partition is used. So input array partition the two parts. Okay, so this is the property of two subarrays. And actual code is this one. Okay, so this code we'll see in this class. Okay. Pseudocode of quicksort function. If there is more than one item in values array, first through values last. Okay, so first index is the beginning of values. Last index is the end of value. So we can call select split value. So this one is a pivot value. Criterion to split the two parts, left hand side and right hand side. So split the array values so that values are first through values split point -1, value is less than equal to split value. And split point value is equal to split value. The second partition, values split point +1 through values last. These arranged values are greater than split value. This split part performed after that we can call quicksort with the left half array and quicksort the right half array. Let's take a look at partitioning by split value in split point. Okay, so the basic idea using split point corresponding value. So left hand side less than or equal to split the value, and right hand side is greater than or larger than the split value. So operations in partition. So initialize this input array. So the first one is a pivot value. Okay, split the value. Index is saved first, and then second one is first. This last one. Okay, and then the idea is we increase the first index until first value is greater than split value. Okay, we can move, right? So 20 is greater than 9. Similarly, we decrease the last index until values of last is less than or equal to split value, like this. Okay, and then so this one is less than 9. Okay, after that we can swap. Okay, swap to value, and then increase the first, decrease last. Their first last is close to each other. Okay, and then last the first, and then right. So last and first is you can crossing. Okay, so this is the ending condition loop. Okay, and then after that last split the point value. This one is actually save the first, right? So say first value is pivot value, and last is actually the first. Okay, the value for the partition left hand side. Okay, so and then this value is swap. Okay, so we have this one. So this result case, you can see this is pivot split point, right? So left hand side, this part is less than or equal to this one, and this one is greater than this part. So divide and conquer in quicksort, we have some idea, variation, how to implement partition. Okay, so the algorithm textbook written by MIT. So the idea is they are using 4 areas: divide, conquer, combine. So the left hand side, this one is X is right hand side, rightmost. This one is a pivot, different from previous example, right? So we can select the first one, last one, doesn't matter. So this part is less than or equal to x, first partition. And this middle case, this partition value is greater than x. And then third region is unrestricted, not sorted items, okay? So we can partition input array, start index is P and the index is the R. We split into two sub arrays, okay? P, Q minus 1, okay? And actually Q is actual pivot. After partitioning, this is a pivot. And then, so we call the quicksort with this left hand side and quicksort call with the right hand side, okay? So first part element is less than equal to pivot value. Second part element is greater than pivot value. So conquer case sort the two subarray, two partitions, okay, by recursive calls to quicksort. Conquer. Combine, no work to combine. It is called the in-place sorting, unlike merge sort. The input array A from P through R is already sorted. Note that in-place sorting is sorting without any extra space requirement. This is different from merge sort. Merge sort require additional memory to merge two subarrays. Okay, let's take a look quicksort pseudocode, okay? So quicksort, input array, this is start index, and A dot length is end index, last index, okay? So we call quicksort. So as long as the start index less than end index, so we can perform divide, conquer, and combine. So we partition is divide, and then we can conquer sub problems with the left partition and right partition. And then okay, divide case, we can divide two partitions using this one. So the idea of this algorithm case, we select pivot rightmost R index item, and the I is end of a first partition, initialize the P minus 1, this part. And then the idea is J is, this one is, you can see unrestricted first index, okay? So we start J is the P, okay? This is because the from first item through before the pivot item, they are not sorted. It is unrestricted element, right? So we increase JP through R minus 1, P and this one R minus 1. And then we can compare that AJ, the element is less than equal case, we can, okay, swap, okay? So increase the I plus 1 index, the I, remember this is the end index of a first partition, right? So we increase I and exchange this, the I, this one, and then the J is currently compared one, right? Compared one, this is a compared one, and the end, this one is if this value, this value is greater or less than or equal case, this value and this value can swap, okay? And then this one is moving here, and the I index is here, okay? And so the I index is we can increase by 1. So like the this part, and less than this part is swapped because I increased it by 1, right? First, and then this one, because this area value is greater than x, and this is less than equal to x, so it should be the partition of first part, okay? So we iterated this one, and then we have first part is value is less than equal to x, the second part element is greater than x. Okay, and then so we can pivot location is I plus 1. So this one is I plus 1. Okay, I plus 1, and this one is switched. Okay, so because the first part and this one is beginning of second part, the pivot, this one is greater than this one, right? So that's why this value going to this value going to this, and then we have 3 partition. This is left partition, this is a pivot, and the right side partition. And then return I plus 1 is this one, pivot the index, right? So previously the P is pivot index. So left partition is P through Q minus 1 is left partition. P plus 1 through R is right partition. Okay, so iteration is R minus 1 minus P plus 1. This one is R minus P. So this iteration is approximately n. Okay, so all partition is considered. This one is we can say n. So 2 cases. Okay, so case 1 is AJ is greater. This value is greater. This one case just increase right hand side. Otherwise, less than equal case, this one value and this one value is swapped, right? So I increase I plus 1. This value is moving to this value moving to this. Okay, and this value is moving to this. Okay, so example is you can take a look. Okay, so remember the array A, P through R is partitioned into 4 regions, including empty region. First one is less than equal to the pivot value. The second partition is greater than pivot, and this is unrestricted region, means unsorted element region, and this one is a pivot. Okay, so loop environment for partition case, the unchanged property. So you can see the first partition case, the value is less than equal to pivot value x. Second partition is greater than pivot, and the pivot position case AK and pivot value x same. Okay, so we have case 1, case 2, case 3. So performance case, worst case partitioning, best case partitioning, and balanced partitioning. So worst case partitioning, when the input array is already completed sorted, okay, such as either non-decreasing order sorted or non-increasing order sorted, already sorted. The partitioning function produces one subproblem with n-1 element and one with 0 element. Okay, why is this the worst case? For the unbalanced partitioning, the recurrence formula for running time, so Tn decompose into Tn-1 plus T0, because of this is subproblem n-1, this is 0 element, and this is combined cost. Okay, so 0 is we ignore, and eventually this is time complexity, right? So eventually this is n square. Okay, best case partitioning, when partition produces 2 subproblems with almost the same input size. One is of size n over 2. This is okay, plowing. The other also similar size. Okay, in that case size n over 2 selling. So why? For the balanced partitioning, the recurrence running time is original problem input size n, 2 subproblem input size becomes a half. That is n over 2, and this is combined cost. Okay, so using recursion tree, we can calculate Tn is time complexity n log n. Balanced partitioning, except for the already sorted case, most of the inputs have a good average case running time. Okay, the average case learning time is much closer to the best case than to the worst case. Okay, let's take a look. The rationale of a good average case learning time: a certain level of unbalanced partitions are tolerable for the learning time zeta and log n. So let's take a look the case of 9-to-1 partitioner split. Okay, 90% left hand side and the 10% is okay right hand side. Okay, partition, something like that. So 10% and the 9%. So we can keep going. Left most case just 10%. Right is 90%. Okay. So in that case, we can calculate this sort height of the partition. We can calculate the depth is log 10n. On the other hand, the deepest one is we can calculate the log 10 over 9 base and n. So approximately the number is n log n. So you can see unbalanced case, not sorted case, right? So in that case, unbalanced case can be accommodated by quicksort. The intuition for average case, a mix of good and bad split by partition. Some of the splits will be reasonably well balanced and some will be fairly unbalanced. Those good and bad splits are distributed randomly throughout the tree. So case 1 like this. Okay, so in that case the bad split and then good split, right? So this is a bad split and good split. So this adjacent level, the combined cost is the zeta n, right? This one zeta n. So good split case, this one is a zeta n. So overall, the another layer, another zeta n is not big deal. Okay, so combine the partition and the merge cost is zeta n. This one is partition and the merge cost is zeta n. So no difference. Okay, so the idea how to avoid the sorted case. We can use a randomized version of a quicksort. The idea is that for good average performance, assure that all permutations of the input numbers are equally likely. This results in well-balanced split by partition. So for this purpose, we randomly pick a pivot instead of a static pivot. First, left-hand side or right-hand side, leftmost, rightmost, such as a R in array A from P through R. So randomized quicksort case, we pick partition with the randomized. So first line, we randomly select pivot index and then exchange the rightmost element and the pivot element, and then we can return. We can call partition, call, and then return, right? So pivot value can handles the case of already sorted case. Randomize the quicksort case, this randomize the partition call, and then we can call recursively randomized quicksort with left half and randomized quicksort right half. Conclusion: quicksort is a fast in-place sorting with divide and conquer. In-place sorting does not require extra memory for merging, combine, like merge sort. Secondly, divide and conquer uses recursion. Time complexity of a quicksort: average case is zeta n log n. Worst case is already sorted input case, zeta n square. Finally, randomized quicksort can handle a special data set like an already sorted one. So if you have a question, please let me know. Thank you for your attention. Bye.